In this presentation, we will discuss the concept of Fourier series. At first, we will show that any mathematical function can be represented by its Fourier series expansion. Then we will learn what is a Fourier series. We will analyze each term in the series. We will also try to understand the behavior of these terms as the series is expanded at a given point. We will also try to understand how terms of series change as the series transitions from one term to the next. Any function can be represented by an infinite series of sine and cosine ratios. If the coefficients and the arguments of the sine and cosine functions in the series are chosen in a proper way, the sum of series gives the value of function for any given input value. The phenomena of representing a function as a sum of sine and cosine ratios can be understood by an example. Consider the graph of the function y equal to sine of t. The graph of this function is a sine wave as shown in the diagram in the slide. The value of y at each value of time is given by the sine value of t. The wave starts at 0 amplitude at time t equal to 0 and sinusoidally propagates through time. Also consider another function y equal to sine of t plus pi by 4. The graph of this function is also a sine wave, but the graph is shifted to the left by pi by 4. This means that this wave is at a phase difference of 45 degrees from the previous wave, as we saw earlier. Amplitude of both of these waves is 1. Now we place both the sine waves at a common time axis. Here the red wave represents the function y equal to sine of t, and the blue curve represents the function y equal to sine of t plus pi by 4. If we add the magnitudes of both of the function, we get another wave shown in color black in the diagram. We see that by adding two sine waves, we got a new function. In a similar fashion, any given function can be represented by a linear combination of infinite number of terms containing sine and cosines with appropriate coefficients. Now consider the situation from another point of view. What will be your idea if we have only the black curve given to us and we are asked to write its function? We can answer this problem in different ways. We can measure the values of y at some suitable points in time. Then we can make a table showing the time values and corresponding y values. We can also try some other methods like polynomial curve fitting, etc. But we will not discuss these topics here. One solution to this situation is to determine the relation y equal to sine of t plus sine of t plus pi by 4. We know from our previous discussion that this relation defines this function, the function given by the black curve. In the present case, we know this, but in general, we will not know this type of relation for any given curve. If we do not know that this function is defined by this relation, how we can get this relation by the given black curve? Fourier series provides us a method by which we can determine the function of any given curve or a set of data by representing the function as a sum of series. This is the general form of Fourier series. Here the first term is a naught over 2. We will discuss the method by which we can get the value of a naught. The second term is a series of cosine ratios. The argument to each cosine function in the series changes term by term within the series, and also with the values of x. The coefficient values for cosine function also change from term to term. The relation given below the series gives the value of coefficient at any term. The third term is a sine series. The argument to each sine function also changes similar to the argument of cosine function in the second term. Also, the coefficients of the sine function vary term to term in the same way. In order to understand the concept of Fourier series, we need to understand the concept of periodicity and periodic functions. A periodic function is one which repeats its values after a fixed increment in its argument. In the slide, we see that a periodic function is one for which f of x plus capital T gives the same value as that of f of x for all x in the domain. As an example, sine and cosine functions are periodic with period 2 pi. We see that value of y1 is 0.5. We also see that the value of y2 is again 0.5. The difference between y1 and y2 is the argument of sine function is added by a value of 2 pi. Similarly, we see that y3 is given as the value of the y3 is 0.5. And the difference between y1, y2 and y3 is just in the argument of sine function. y1 is just pi by 6. The argument of y1 is just pi by 6. Argument to y2 is pi by 6 plus 2 pi. And the argument to y3 is pi by 6 plus 4 pi. So we see that the argument of the sine function is changing by a multiple of 2 pi, and we are getting the same value of the function y1, y2 and y3. Now we will examine the terms of the Fourier series in a little bit more detail. The first thing to know is the leftmost term, which is f of x. F of x is a general notation which is used in mathematics to denote a function of some variable like function of x. For example, if we have a function y equal to f of x equals to x square, we normally say y equal to x square. Sometimes we say y equal to x square, and sometimes alternatively we use the notation f of x is equal to x square. All that means is that f of x is a function which defines the value of variable y as a function of variable x. Fourier series expresses y equal to f of x like the same function as we saw above as a sum of infinite terms. These terms are sines and cosines with suitable coefficients, which we will see in the coming slides. The first term on the right side of equality in the Fourier series is a naught over 2. This is the first term of the series. All the terms in the series are either cosine or sine functions, except the first term. The first term is a naught over 2. The definition of a naught is as follows. We can see on the screen that a naught is defined as a naught equals 1 over L times integral of f of x with respect to x from limit negative L to the positive L. This means that we are integrating the values of the function for which we are expanding the Fourier series from negative L limit to the positive L limit. These negative L and the positive L are the extremes of the period, which means the period of this function should be 2L. And we also observe that we are dividing that integration term by L, which is half of the period. So This gives us sort of a weighted average of the function values over a period, over the entire length of the period, which is 2L in this case. Now we will focus on the other terms in the series. We see after the first term, we have two sets of terms in the series. The first set is summation of the terms containing am cosine of m pi x over L, where m is changing from 1 to infinity. And the second group of terms is a summation of terms containing bm times sine of m pi x over L, where m is again changing from 1 to infinity. These are the series consisting of cosine and sine functions. The first one is the series consisting of cosine functions only, and the second one is a series consisting of sine functions only. In the next two slides, we will examine the nature of argument to sine and cosine functions, and also we will examine the definition of coefficients am and bm, how they behave when we progress in the series. In this slide, we will examine the arguments of cosine and sine functions in Fourier series. The argument of cosine and sine functions in the Fourier series consist of the term m pi x over L. The term m pi x over L contains four parameters, that is m, pi, x, and L. Pi over L remains constant for all terms of the series for a given function. M is an integer. The value of m changes from 1 to infinity, and this is the number which gives the position of a term in the series. This means that the value of m for a specific term remains the same in any expansion of Fourier series. This means if we expand a Fourier series at some value of x, the value of m for a specific term remains the same if we expand the same Fourier series at another value of x. X is the independent variable of the function whose Fourier series we expand, which means x is the value of the independent variable. Like if we have a function y equal to f of x, so x is the value of the x coordinate in that function. Now we will examine the coefficients of cosine and sine functions in Fourier series. The coefficients are defined by these relations. An is equal to 1 over L integral of f of x times cosine of n pi x over L dx, and the limit of integration is from negative L to plus L. Same way, Bn is given as Bn equal to 1 over L times the integration of f of x sine of n pi x over L dx. Limits of integration are from negative L to plus L. Now we will analyze the coefficient terms. Coefficients are obtained by integration of the reduced values of the function over the length of one period. We have seen in the previous slide that the coefficients were given by an integration process, and the integration was from negative L to the positive L, which is the length of the period. However, the values of the function in each integration were being reduced by a suitable factor. We saw that the sine function in the previous definitions was responsible for this reduction of the values of the function at every x. Now we try to understand the variation of coefficients within the series. We know the series consists of infinite number of terms, so we want to determine how the value of the coefficient for cosine and sine functions vary term to term. To understand this variation of the coefficients within the series, we need to understand and analyze the definition of the coefficients without parameter n. If we remove parameter n from the definition of the coefficients, we observe that the coefficient definition of the coefficient reduces to the one given on the screen, which says an is equal to 1 over L times the integral of the function times cosine of pi x over L, where the integration is done from negative L to the positive L. Similarly, Bn is given as Bn equal to 1 over L times the integration of function of the x x times sine of pi x over L dx, where again the integration is done over the period from negative L to positive L. We observe that n doesn't show in these relations. Normally, if we write regular definition of the coefficients an and bn, the term n appears in the argument of the cosine and sine functions, and it reads like n pi x over L. But we observe here we don't have n pi x over L in the argument. Instead, we have just pi x over L in the argument of cosine and sine functions. Because we are integrating the function from negative L to L, so we observe here that argument to the cosine and the sine function will vary with x only. It will not vary with n. Also, the second factor within the integration is f of x, which again changes its value with x only. It does not depend upon the value of n. So all this means is that if we will write the coefficients for any term in the series, because the coefficient does not depend upon the value of n, so the coefficients for all the values all the terms of the series will become same. All terms of the series will have same coefficient value, which is not true. However, this method and this new definition without n, which is not a correct definition, but it gives us an insight that how the coefficients of the terms, they vary depending upon the value of n, and n is the position of the term in the series. Now we will focus our attention to the role that even and odd functions play in the expansion of the Fourier series. Uh, Before we can understand the role of the even and odd functions in the series, we need to understand what even and odd functions are. By definition, an even function is defined as f of negative x is equal to f of x if some function satisfies this condition within the domain of the function, then that function is called as an even function. This means that if we replace the argument of any function by its negative or the additive inverse, the value of the function does not change. This type of functions are called as even functions. The other type of function is the odd function, and the definition for the odd function is given as f of negative x is equal to negative of f of x which means if we replace the argument of a function by its negative or by its additive inverse, the value of the function becomes also the additive inverse of the original function, which means if the original function value was positive, after replacing the argument by its negative value, the value of the function also becomes a negative value. This type of functions are called as odd functions. We will discuss the role of odd and even functions in the solution of uh, in the expansion of the Fourier series in a while. But before we do that, we need to have a look at our objective in Math 391 00 class. So in 391 course, for the Fourier series chapter, we will be normally given a function, a well-defined function will be given to us. And based on that function, we will be asked to find out the Fourier series for that function. That will be the assignment which will be given to us. So our task is to determine the coefficients of the series and write them in the series with their respective terms, which means that our main job is to get the values of the coefficients for the series. If we know the coefficients of the series, we can just replace those coefficients with their respective terms and write simply the expansion formula of the series, and that will give us the series for that particular function. Now comes the question of our approach, that how we will tackle these problems when we will face them. So the first step in our approach will be to determine the period of the given function. In normal cases, the period will be indicated by an interval such as from negative L to positive L, x is greater than negative L and x is less than positive L. But it will be, most of the time it will be given as a part of the question. So we have to decide on the period of the function, that what is the period of this function. Second step will be that we will be checking if the function is even or odd. So after the period is known, we will just check whether the function in question is an even function or it is an odd function. So this is the point where these functions, their nature, whether being odd or even, plays a role in the solution. If the function is an even function, we expand only the cosine series, only the terms containing cosine ratios. Those terms will be expanded and we are supposed to get the coefficients for only those terms, because the coefficients of the sine terms, they just become zero and we don't need to write them, so we just expand the cosine series. If the function is odd, in that case we will expand only the sine series, and of course we will have the first term also. So that is why we defined earlier what is an even function and what is an odd function, because these functions, if we know it is an odd function or we know it is an even function, that simplifies our solution and we have to solve for only half of the series. So based on our determination that whether it is an odd function or even function, or whether we need to get a cosine series or a sine series, we will determine the coefficients of the terms by using the formula which we already have discussed. And once we know the coefficients of the terms, we will simply write them, write the terms, write the cosine or the sine ratios with their appropriate coefficients, and that will be our solution. Now we will solve an example problem from the textbook. The given function in the example problem is f of x equal to x. The domain for the function is negative L is less than x is less than L. If we draw the function, if we draw the graph of this function, we see that this function is a straight line at an angle of 45 degrees with the x-axis. At x equal to 0, the value of y is 0. Therefore, the function crosses through the origin, as we can see in the diagram. For values of x greater than minus L and x less than L, this definition of the function, that is f of x equal to x, is a valid definition. However, at x equal to minus L and x equal to L, the function is defined to be 0. Hence, at x equal to minus L and x equal to L, the function is discontinuous, as we can see in the diagram by the two circles at the extremes of the blue straight line. We also know that this is the given statement in the problem, that the function is periodic with the period 2L. The task in this problem is to write the Fourier series of the function. The first step in the solution is to determine the period of the function. The period of this function is 2L. How we know it is 2L? In this case, the statement of the given problem explicitly tells us the period of the function. However, this will not always be the case. If the period is not explicitly given, then we can find out the period from the given interval. We see in this case that the length of period 2L can be achieved by subtracting minus L from L. This means that we can get the period of the function by subtracting the lower bound of the interval from the upper bound of the interval. Hence, we get L minus L equals to 2L. The parameter L used in the Fourier series formula is half the length of the period. Therefore, the value of parameter L in this case remains L. The next step in the solution for Fourier series is to check if the function is even or odd. The given function is f of x equal to x. If we replace all x terms in the function by minus x, we get f of minus x equal to minus x. We see that this result fulfills the condition needed for odd functions, that is f of x equal to minus of f of minus x. Therefore, this is an odd function. Now the function is odd. We know that for odd functions, the coefficient of the cosine terms become 0 in the Fourier series. Therefore, we don't need to calculate the part of the Fourier series which contains cosine terms. We need to calculate only the terms containing sine functions. If the function was even, we would have had needed to determine the cosine series. However, this is not the case for this problem. Now our problem is reduced to determine only the coefficients of sine functions in the series and putting their values in the series formula. The coefficients are given by the relation Bn equals to 1 over L integration of f of x times sine of n pi x over L. Integration is done from minus L to plus L. Within the period minus L is less than x is less than L, the function is defined by the relation f of x equal to x. We will use this definition of the function f of x equal to x, and we will replace the function f of x in the Bn formula by its value x, and we will solve the integration to get the value of Bn. Here the Bn formula is given with function f of x replaced by its value f of with its value x. We see that Bn becomes Bn equals to 1 over L times integral from minus L to L of x times sine of n pi x over L. Clearly we can see that f of x has been replaced by its value x. This is the same relation as we got in the previous slide, that is Bn is equal to 1 over L times integral of x times sine of n pi x over L with limits of integration from minus L to L. In order to get the value of Bn, we need to integrate this integration of two functions. As we can see here that these are two functions. It's basically a product of two functions. One of the function is x and the other function is sine of n pi x over L. For these two functions, we can apply the technique of integration by parts. When we apply the integration by parts technique and solve this integral function, we get this relation. It says Pn is equal to 1 over L times uh, x times minus cosine of n pi x over L divided by n pi over L with limits minus L to L minus integral of negative cosine of n pi x over L divided by n pi over L with limits negative L to L. These two terms in the brackets are basically two parts of the integration by parts formula. So in the second part, when we have the integral, we are left with only one term. Theoretically, we were supposed to have two terms, but the second term is derivative of x with respect to x, and it becomes 1, and therefore we didn't write that one. So we are having only one term in the integration on in the last part. In the next step, we will we have used the limits of integration for the first half of the right side, and for the second half of the right side we have solved the function by using the uh, trigonometric relations of integration. So in the first half we get Bn equal to 1 over L times negative L over n pi times L cosine of n pi L over L plus L cosine of negative n pi L over L. This relation, there are two important points to note, that the factor L over n pi in the beginning of the relation is just the inverted denominator in the from the second line. We have n pi over L in the denominator in the first half of the right hand side relation in the second line. So we get this n pi over L and out of the bracket, and we get when we invert it we get L over n pi. Rest is just we are plugging in the limits. The negative sign from the formula becomes positive sign because of minus L. On the right hand side of the in the second half of the right hand side, when we integrate minus cosine n pi x over L, so we get a function sine n pi x over L and divided by n pi over L. So when we will put the limits in this relation, we will see here that the right second half becomes L square over n square pi square times sine of n pi plus sine of n pi, which is basically 2 times sine of n pi, but we know that sine of n pi is always 0, so we don't write anything after this relation, which we can see on the screen. So we will not write anything for the second half of the right hand side, but for the first half of the right hand side, the relation turns into uh, negative L over n pi times 2L cosine of n pi. So when we simplify this relation, it further simplifies to become Bn equal to negative 2L over n pi cosine of n pi. One of the L in the numerator gets cancelled with one of the L in the denominator. We know that cosine of n pi has only two values because n is an integer. So if n is an even number, it becomes a multiple of even multiple of pi. So it's the cos of n pi becomes 1. But if n is odd number, so the argument to the cosine function becomes odd multiple of pi. So the value of cosine of odd multiple of pi is negative 1. So this function basically alternates between +1 and -1. So instead of writing a cosine of n pi, we can simply write it minus 1 to the power n. This will give us the same values alternatively as we will change the value of n. So here n is an integer, its value changes from 1 to infinity. So now we got the relation for Bn in the previous slide. Now we will use that relation in the Fourier series, and we will write the Fourier series. As we already have shown that Fourier series for this particular function consists of only sine series. So we have written only the sine series here. So we can see like we have replaced the value of Bm uh, by the relation which we got for Bn in the previous slide. We have replaced Bm by that value, and we have written this series, which is Fourier series for that given function. We are using notation m here in this series, but we were using in some of the slides notation n. This m and n are basically the same number. This is the same exact thing. In some of the slides we used n just to distinguish the sine and cosine ratios which were being used to calculate the factors, and not the factor, to calculate the coefficients. So we have used at some locations notation n, but n and m are basically the same number. They are not different, they are the same thing. So we get the relation for Fourier series of the function f of x is equal to summation of minus 2l over m pi times minus 1 raised to power m times sine of m pi x over l. We see that there is a minus sign before the coefficient 2l over m pi. So we can shift this minus and combine it with the minus 1 raised to the power m term, and we can write a single term as we see in this relation, that we have shifted this inside the minus 1 raised to the power m term, and it becomes minus 1 raised to the power m plus 1. So this is our final version for that Fourier series which was required for that function. In this presentation, We observed that any function can be written in the form of a Fourier series. We also saw that the general form of Fourier series is given by this formula, which says f of x is equal to a naught over 2 plus sigma am times cosine of m pi x over L plus sigma bm times sine of m pi x over L, where m goes from 1 to infinity. The problems on Fourier series can be solved by determining the coefficients of the sine and cosine functions in the above formula and writing the above formula with the appropriate coefficients. The values of appropriate coefficients a0, am, and bm can be determined by using the formulas given in this presentation in earlier slides. Thanks for watching this presentation. This presentation was presented and prepared by Muhammad Attiyab as a part of Zitten Scholarship Award. Zitten Scholarship is awarded to extremely brilliant students who are part of Students Sports Services Program at the City College of New York. The program helps students at the City College to succeed in their career goals through peer mentoring, tutoring, academic advisement, career counseling, and other sub-projects. The details of the activities of SSSP can be seen on the official website of the City College of New York. For any questions regarding the SSSP program or its activities, you may contact Student Support Mr. Tyson Ward. Mr. Tyson Ward can be reached by his office phone number 212-650-7055. He can also be reached through his email tward@ccy.cuny.edu. You can also physically visit his office at MR 1104 at Marshak Building in the City College of New York during the regular working days. Thanks again for watching this presentation.